Pascal's principle states that pressure applied to a fluid is transmitted undiminished to every point and to the walls containing it, even if that pressure is applied in a very small area. The pressure will be transmitted to potentially much larger area if the fluid is contained. And a dramatic demonstration of that allegedly took place in 1646. Historians are not 100% sure based on the historical record whether or not it actually took place or if it's just kind of a story that got invented afterwards. But this is a picture here of what I'm describing, which is Pascal doing this demonstration of his principle. He has a wooden barrel down here, kind of in between his ladder there, and he has a pipe that is connected to it in a way that is sealed, and it's a very long and narrow pipe. And at the top of the ladder, he is pouring in a little bit of water into that pipe. And if the barrel starts out filled with water, and then he simply adds enough water to fill the rest of the pipe, that winds up applying a pressure to the top of the barrel that's really a function of the height of water in the pipe, because a pipe is like a narrow water column. But that increased pressure winds up being distributed undiminished to the walls of the barrel, and the barrel winds up failing. So you can see there, I think there are some holes and water is starting to come out. And that's dramatic that could be done with such a really maybe simple and not really brute force looking type of action could break this really sturdy looking barrel. The concept of Pascal's principle applies to modern devices like a hydraulic lift, like is shown in this sketch right here. This is a very simple sketch without a lot of details, and it's maybe a little bit better than some of the ones I'm going to hand draw in some of the examples. But the idea is there is a cylinder at which you apply a force which can increase the pressure in the fluid that's here in this hydraulic system. And that pressure winds up transmitting undiminished and could lift up a car, even if the force that I apply here is much smaller than the weight of this car. And the reason why is since a pressure force is equal to pressure times area, if the part that is lifting the car has a much larger area, there will be a much larger force transmitted to this part of the system as compared to what I have to apply. A simple formula for that is listed here on the key concepts page. It says F out, that's what that means, FO is F out, is equal to the ratio of area out to area in multiplied by the force in. So if the area out is much larger than area in, this results in a large multiplication of the force, or basically a large increase. You could say magnification. I like to say force multiplication. This is like a force multiplying system. I put in a force, and if this area is 100 times larger than the area at which I applied the force, I would get 100 times force multiplication. That formula is based on pressure, though. The concept is that the pressure... Oops, hang on, let me make sure I have the correct pen tool here. And the correct end of the pen. Okay. Pressure out should be equal to pressure in, which means that force out divided by area out should be equal to force input divided by area input. And this statement is algebraically equivalent to the second bullet on the key concept slide. If I multiply both sides by area out, I believe this winds up being the same as this one here. You can analyze a system like this in an alternate way as well by saying that the work out, in other words, the work done by the output force is equal to the work done by the input force. And that would look like force out times displacement out, since work is force times displacement, is equal to force in times displacement in. And if you take this formula and divide both sides by the XO that represents output displacement, you get the last formula here on the key concept slide. So these two formulas are useful for analyzing systems like a hydraulic lift, or another example would be a hydraulic braking system.